Here we're continuing our discussion of network infrastructure, in this case specifically layer 3 network devices, and we're looking at routers. So as we said, a router is a device that connects different segments together, and each of those segments will typically have at least one IP subnet associated with it. And a router knows about the subnets that it has nodes, that it has network interfaces attached to. So as we look at the diagram on the right-hand side of this slide, we see that router A in the upper left-hand corner there has a network interface on 192.168.10, and his IP address is 10.1. He also has an interface on 192.168.12.1, 192.168.11.1, and 192.168.15.1. So router A knows about those four networks because he has those .1 interfaces on each of those IP subnets. However, router A doesn't know anything about the 13.0, 14.0, 16.0, 17, 18, 19, 20, 21.0 networks that are attached to other routers B, C, and D. So we have to teach router A that if one of the nodes on one of his subnets, 10, 11, 12, or 15, want to communicate with, let's say, a node on the 19 subnet, router A has to know a path to get to that 192.168.19.0 network. So we have to teach him using a specific command if we're going to do static router addressing. And we use a route-p add statement on router A to teach it about those other networks and how to connect to those other networks. So let's walk through how this works. If we have a node, let's say at 192.168.10.25, and it wants to send a frame to a node at, let's say, 1.2.168.13.55, we have to teach router A that if you want to get to that 13 network, you have to send the frame out your 192.168.11.1 interface to the gateway of 192.168.11.2 interface on router B so that it can then forward your frame onto 192.168.13.0 network. And that is the process we have to go through for the 13, 14, 16, 17, 18, 19, 20, and 21 subnets. So we would have a series of route-p add statements. By the way, the -p says make this route persistent. In other words, store it in memory. Even if the router is rebooted, bring this route back. Remember this route even if the router gets shut down. When it powers up again, remember this route. I don't want to have to type this in a second time. So the statement is route-p add, the destination network address, the mask, and the subnet mask, and this is in dotted decimal form. And then what is the gateway, the interface on the adjacent router that you want to send this frame to in order to connect to that remote network. And that last statement is metric. Consider that to be the number of hops from this router to that destination network. Each router is considered a hop. Now this metric function also allows me to assign a cost to the route. As I maybe artificially inflate the metric, I'm saying this is not a preferred route. The routers will always send the packet through the route that has the lowest possible metric and will only roll to a higher metric path if that lower metric path is not available. So let's walk through the way this works. If I'm going from 192.168.10.25 to 192.168.13.55, I need to teach my router the following route. Route-p add 192.168.13.0, that's the destination network. The word mask and then the subnet mask for that network address is 225.225.225.0. That, by the way, is a /24 mask. And then I have to tell router A what is the interface on the adjacent router that is your path to that 13.0 network. Well, in this case, router A has to send the frame to 192.168.11.2 on router B. because router B is attached locally to that 13.0 network. And I'll also tell router A that it is one hop to that 13.0 network. Now again, if I wanted to, I could steer the traffic down through C over to D and back up to B, but then I'd have to say a metric of 4 for this particular route that I just typed in. And now the 3-hop route down to C, down to D, and then up to B, that would be 3 hops. So the cheaper path is that CDB path. However, if that path gets broken or interrupted some way that I can't get through on that path, I'll roll to the metric 4 path straight from A to B rather than through that longer loop. Now, why would I do that? Suppose that 192.168.11.0 segment is a slow dial-up or it's heavily trafficked and I don't want to put any more traffic on it. So I can steer the traffic around that 11.0 network by adjusting the metric for the route mapping. So as you can see, we've added mappings for the 14.0 network and the 16.0 network. All this is done on router A. I'd have to go to B and C and D to teach those routers about the networks that are not local to them. As we look at router B, he's local to 11, 13, 14, and 16. But he doesn't know about 10, 12, 15, etc. So we'd have to go do a route-p add statement on router B for each of the networks that he does not have network interfaces attached to locally. Now, continuing on, what we just did was static routing. We can configure our routers so that they communicate autonomously amongst themselves and share this route table information amongst themselves. What a great idea. So now I don't have to go do that route-p add statement 63 times on 4 different routers. I can program these routers to use the same dynamic routing protocol, and I configure the protocol on each of these routers, and now they will communicate amongst themselves. There are primarily 2 different families of algorithms that dynamic routing protocols utilize. They either use a distance vector algorithm. Typically, this is only used for small networks, like up to maybe 15 nodes, 15 routers. And the larger of the 2 is called link state algorithms. This is used for medium and large networks. This is what the internet uses to communicate the route tables amongst the many, many, many routers on that very large public internet network. And you'll see a reference of a handful of the different routing protocols. RIP, that's the router information protocol, RIP v2. Down below we have the link state algorithm is open shortest path first protocol. Now again, that's the one that gets all the business on the internet. And again, the routers only know what they can figure out on their own through the dynamic routing protocols or what a administrator types in statically. And there is a potential that a router could establish a loop called a routing loop, where a packet hits a series of routers and actually never makes it out of the loop. In other words, it just continues endlessly until the router is discarded due to its old age. So there are several techniques that are used on routers to avoid this routing loop problem. And one is called the poison reverse, one is called a split horizon, and another uses something called hold down timers to avoid these routing loops. We'll take a quick break here and we'll pick up where we left off shortly. In this lesson, we're going to be discussing firewalls. Firewalls are network infrastructure systems that generally establish the boundary between different areas of the network that have different levels of trust. In other words, on my intranet, I have a high level of trust for all the nodes that are there because these are my employees and these people have to come through the security control at the front where the security guard is. They have to show their badge. They have to go to their cubicle. Their fellow workers would recognize who they are, et cetera, et cetera. So I've got all these physical controls in place. And the users in this computing environment are relatively trusted. However, our network attaches to the branch office. Well, we don't know those people quite so well as we know the people in our office. For all we know, that branch office has been compromised and there might be some user in that branch office that isn't authorized to be using the computers. So what we do to defend ourselves from these lesser trusted computers and nodes and users is we separate our intranet from that extranet with a boundary, a security device called a firewall. So the firewall is typically a routing type of a device. It's not exactly a router, but the original firewall was a router. It had an application added to it that did filtering. And so you can assign an access control list to the firewall that says disallow this type of traffic. And that could be based on its IP address. It could be based on port numbers. It could be based on protocol. And then some. We'll talk more about these as we look at the chronology of firewalls. Now, this device that we're talking about is typically a piece of hardware, a dedicated appliance. It can be an application on a computer, but typically a firewall is sophisticated enough. I'd rather buy a dedicated appliance that does nothing but firewall functions. And if I have a firewall on a computer, it's called a personal firewall, and it's just to protect one node, that one host. So that's a different type of firewall altogether. We'll talk about them in a few minutes. This is an appliance that typically will have multiple network interfaces, typically at least 2 and sometimes 3 or 4, depending on the number of demilitarized zones or screened subnets that we might want in our networking infrastructure. So we call a device with multiple network interface cards a multi-homed system. In other words, it has a home on this segment and it also has a home on that segment. And it establishes a connection point between those two segments, but it is a security device who is programmed to do filtering. It is also a hardened called bastion host system, which means from one side, it's very difficult to penetrate. So it has a hard, crunchy outside that points out towards the public side, the less trusted side. But then on the inside, it might be a little softer and chewier because this is the trusted environment on the inside. So the firewall will typically have a public interface that is the hardened interface that has a default deny all rule built into it. And then it has a more gentle interface, the private interface, that points towards the trusted networking environment. So again, the firewall is used to establish security zones between networks of differing trust levels. And as you can see, we're going to quickly review 5 generations, the evolution, if you will, of firewalls and firewall technology. So let's move forward here. The first generation firewall was called a packet filtering firewall. Now, these are still around. We still use these on a regular basis. Basically, the packet filtering firewall is a layer 3 router that also has an application on top of it that allows me to add an access control list that can filter traffic out that I don't want. So based on IP address, based on port number, and based on protocol and direction, I can establish this packet filtering firewall. I'll build these rules in what's called the ACL, the access control list, and I can allow traffic that I think is good, and I can have the firewall drop all the traffic or block or deny all the traffic that I think is bad. Now, the problem with the packet filtering firewall is it was just a little bit dumb. It was fast and it was strong. It was hardened, so the bad guys couldn't break into it very easily. But the problem is it's only got a go, no-go capability. It's only red light or green light, and there's not much in the middle. So because we have to use the range of port numbers, if you recall, we have server-side port numbers that are the destinations of services that I'm requesting. And then we have the client-side port numbers that are pulled out of the ephemeral port number range that would range from 49,152 to 65,535. That client-side port number range had to be open 100% of the time. So there's a huge hole in your firewall. Imagine you build a fortress, but you leave a 200-foot gap in the wall. So you got 3 sides that are all wall and one side is missing. That's not a very strong fortress. So while it did do some blocking of some port numbers, there were so many port numbers we had to leave open because of the way the client-side port number is randomly selected from the ephemeral port number range. They weren't great when it came to overall security. They were better than nothing. They were our first generation of firewall, but they still had some problems. Again, because this was built on a router, this was a layer 3 network device. It made its decisions primarily based on IP address. It understood a little bit about MAC addresses, so it could do some stuff with MAC addresses, again, depending on implementation. And it understood only the port number. It didn't understand what the port number meant, but we could say anything to port 25, green light, anything to port 443, red light. And so while it could see a number and a go, no-go port number, which is layer 4 functionality, it didn't understand what that number actually meant. It was just red light or green light on that port number. So it didn't really understand layer 4 protocols. That's why this guy still lives at layer 3. Packet filtering firewall also didn't have any way to correlate series of packets. So it couldn't understand a flood type of attack. It couldn't understand a fragmented attack. So payloads that were malicious in nature would still sneak through this firewall because he had no way to put these pieces together and actually look at the picture and figure out, ooh, this isn't good. Stop this stuff. Basically, he was real basic. He could look at one packet at a time and give it a red light or give it a green light. Because this was a filtering device, it created what we called a screened subnet. And anything behind the firewall on the private side was a screened host. Anything on the other side, of course, that's the less trusted public area. And I don't care about what happens out there. That's not my turf. Those are the guys I'm defending myself from. Now, in the diagram down below, what we see is a packet filtering firewall placed external to your external firewall. So this did some initial filtering, and this is where we still might use this device, outside the external firewall to knock down a lot of the junk that I don't anticipate wanting to receive in my corporate environment. So I'll use this relatively cheap, relatively fast, relatively strong, but also relatively dumb packet filtering firewall to knock down a lot of the garbage that the public internet is throwing at my external firewall. That allows him to operate a little more efficiently only on the traffic I might consider receiving. So in this case, that external firewall, the EFW, is a screened host being protected by the firewall to the left of him, the packet filtering firewall. We're going to take a quick break here and we'll pick up on Generation 2 firewalls. We're picking up on firewalls relative to network infrastructure, and we're looking at the Generation 2 proxy firewall. Now, the proxy firewall had two different levels of capability depending on what you were willing to pay for. We had a circuit level proxy firewall and an application layer proxy firewall. Let's start with the circuit level firewall first. We'll describe the basic functionality of that guy, and then we'll talk about the increased capabilities and some of the downsides associated with the application layer firewall. So the second generation firewall had the goal of disconnecting the client computers on the trusted private network from the untrusted computers on the less trusted public network. When a client on the private side wanted to access a web server that was out on the public internet, the client literally transmitted his request to the proxy firewall as if the proxy firewall represented the entire internet. So there would be a session established between the client computer and the proxy firewall, the firewall that you built, that you installed, that is part of your security network infrastructure. The proxy firewall, assuming the request was allowed due to the access control list, we might be filtering on a particular component here that the guy's asking for, but let's assume that the request is actually authorized and allowed. The external firewall, in this case, the proxy firewall, would then presume the role of the client on the public network and make the same request of the web server out on the public internet as if the proxy firewall is the client making this request. So as you can see, it actually broke the connection between the true client inside on the private network on the corporate LAN and the untrusted server on the public internet. Now, that web server out there on the public internet would assume the proxy firewall was the real legitimate client requesting information, and it would transmit its data back to that proxy firewall. The proxy firewall might have some rules, once again, that it might filter content on, but let's suppose that in this case, the proxy firewall says, yeah, the content looks good. I don't have any rules that should block this. So now the proxy firewall would act as the web server in this relationship and transmit the data down to the client on the trusted corporate LAN. So the client never actually communicated directly with the web server, and the web server never actually communicated with the client on the private LAN. The proxy firewall acted as the intermediary and broke the connection between those two nodes. Now, the circuit level proxy could have authentication capabilities. In other words, I could write a rule that said Bobo is not allowed to use the internet from 8 a.m. until 12 p.m. And if this particular request came from Bobo and was going to the public internet, I could now first authenticate Bobo, be sure I know who it is because I've got rules now that say this guy can go and that guy can't go. And I'd authenticate who Bobo is, and then I would look for any rules relative to Bobo. And if the request came between 8 and 12, which is a deny period, I would simply reject this request, and Bobo would get a web page that said unable to connect to server or something along these lines. So we can use authentication now, the computer's name as the source of filtering. We also then could add to that the source IP address, destination IP address, source port number, destination port number, the protocol used. We can even filter based on domain name. Suppose the client is trying to get to sportsillustrated.com, and I don't want him watching a baseball game on Tuesday afternoon. I want him doing his work. So I might deny all requests to sportsillustrated.com. Oh, except for the senior management team. They can do anything, especially since they have some impact on my salary. So let's give them whatever they want. We'll block it only for the general users, but the senior management team, they can get to wherever they want to go. And I can turn on these filters, these ACLs, access controls, and identify who and what and when. So I have a great deal of control over connectivity out through this firewall. In addition, there are many known bad websites, web servers, destinations out there on the public internet. They have a well-established reputation. These guys are going to send you malicious software, viruses. They're going to try to steal your private information, et cetera, et cetera. So this blacklist, or these blacklists, because there are many sources of these, are published on a regular basis. And so what you can do is configure the blacklist on your proxy firewall. You can even configure your proxy firewall to reach out on a daily basis, download today's blacklist, and now anything on that list, any destination on that list, you're going to automatically deny. So we have this whitelist and blacklist capability. We could turn on a deny all public addresses and names other than those 17 that are on my whitelist. My clients are only ever going to need to go to these 17 places, put them on a whitelist, and then deny everything except those on the whitelist. I can build a whitelist or a blacklist and use this for filtering. Now, because we base the biggest part of our filtering on the IP address and a port number, these two pieces of information collectively form something called a socket. If you recall from earlier lessons, an IP address : port number is a socket. And if I want to consider the bidirectional, the full socket, I would consider the source IP and port and the destination IP and port, and that would be a true bidirectional socket. Well, since the very first circuit level proxy firewalls use primarily this IP address and port number as the filtering tool, they were referred to as SOCKS proxy, SOCKS coming from sockets. And in order for your client computers to use the SOCKS proxy, they had to be configured so that they treated your proxy firewall as the entire public internet. They sent their request to your proxy firewall, who pretended to be the entire internet. That proxy firewall would then filter or analyze that request, and if everything was allowed, that proxy firewall would go to the public interface on the firewall and act as the client. On behalf of the true client, he would then reach out to the public servers and pull that content down. Now, as we move towards the application layer proxy firewall, this guy added layer 7 functionality to the process and could actually reconstruct content that was pulled back down from the public servers and then run analysis, whatever type of analysis was configured and capable of that particular firewall based on implementation. We might do content analysis. And if we found it had to do with gambling or sports or pornography or something else that was undesirable on the corporate network, we could simply deny that content based on the rules for content filtering, based on what that content actually contained. Now, as you can imagine, this reassembly of all the content and then analysis of all that content and then comparing that analysis to your rule base takes a little bit of time. So these application layer firewalls, proxy firewalls, called an application layer gateway, provided deep packet inspection, but it took time. It was slow. And because it was so painfully slow, very often these firewalls would add a caching component to the firewall. So it would be a caching server as well. Now, if the client wanted to go to, let's say, google.com, the proxy firewall would have been there 63 times already today, and he would simply feed the client back the web page that he had already downloaded, analyzed, and then cached. Once it's been blessed, he'd feed it right to him from his cache. So hits from the cache are very fast because he didn't have to reach out and go get a new copy and go analyze it, and et cetera, et cetera. So the application layer proxy firewall, also called an application layer gateway, could do all the things that the circuit level proxy did, including authentication, computer name, source and destination, filtering, IP, port number, direction, domain name, whitelist, blacklist, now content filtering and caching. All these features were available on the application layer gateway. Now, if we were going to reassemble web content, I would have to install the HTTP proxy application. If I needed to reassemble and content filter FTP traffic, I'd have to install the FTP proxy application. So in order to reassemble the content to do the content filtering, my proxy firewall would have to have that application proxy installed on the firewall. If you didn't have that protocol installed on the firewall, that proxy service installed on the firewall, you couldn't proxy that particular protocol. It had those limitations. We will knock off here on the Generation 2 proxy firewall. That's it for now, and we'll come back and talk about more firewalls in a few minutes. We're picking up with the Generation 3 stateful firewall. Now, this was the third generation firewall. We've been through the packet filtering firewall, the proxy firewall. Now we're going to add to it the capability of something called the stateful firewall. This guy added a tremendous amount of capability to the firewall functionality. Remember, the firewall is a security boundary between two collections of segments that have different levels of trust. So this is your security boundary. You have a public side that is untrusted, a private side that is more trusted. And what this guy did is he said basically that everything inbound from the public side is by default denied. In other words, nothing is allowed through the firewall. Well, why not just disconnect the cable then? Well, here's the exception. The only way the stateful firewall would allow a packet through from the public side to the private side is as a client on the trusted inside, the private side, made a request outbound, the stateful firewall would document that request in a state table. It would record the source computer, the destination IP address, the protocol used, the port numbers used, and only if the inbound packet matched an outbound request. In other words, if I didn't request it, I'm not letting it through. Only if the firewall found a mapping on the state table where we actually requested that packet, that's the only time the stateful firewall would open up that hole dynamically, let the packet through, and then close the hole right behind that packet that is allowed. So this added a great deal of functionality to the firewall family. As you recall, the packet filtering firewall simply hardwired port numbers open or closed, and it was either red light or green light 24/7, and there were no conditions. Here, finally, I can say deny all inbound traffic to the client-side ephemeral port number range of 49,152 to 65,535. Deny all that traffic unless that inbound traffic is the response to a request we made from the inside. So this now, collectively, the packet filtering firewall, the proxy firewall, and the stateful firewall, when you add that functionality of those three technologies together on the same firewall, now finally you have a very strong, very secure, very functional security device. So it was only after we got to generation 3 that we really had a pretty good handle on how a firewall should operate. And by coincidence, as I describe putting these together, what we're going to learn is the generation 4 firewall is the combination of the packet filtering firewall plus the stateful firewall. So the fourth generation is, let's put these functionalities together. And we call this a dynamic packet filtering firewall. And that dynamic part is relative to the stateful firewall's dynamic opening and closing of ports only if it's a stateful response to a request we already made. So here we're going to see that I can now support internal services by hardwiring, let's say, port 80 and 443 open inbound, and I map them directly to my web server. And I'll also open port 25 inbound, and I'll map that port number to my email server, and then I'll deny everything else using the packet filtering functionality. In other words, anything that's not something I've requested and isn't going to my web server or my email server, the answer is I'm going to reject it. Oh, wait a second. What about when my clients make a request of something outside? Well, that's where the stateful component of this dynamic packet filtering firewall comes into play. Remember, the stateful firewall says all inbound ports are closed unless I have already recorded on my state table a request that came from the inside outbound requesting that traffic, and only if it's a stateful response to something we've requested that I'm going to allow. However, if it's an unsolicited inbound packet, then I'm going to reject it. Unless it goes to port 80, 443, or 25, those the packet filtering firewall always allow and will steer to either the web server or the email server. And so you see this fourth generation dynamic packet filtering firewall is the bomb when it comes to really what do we need for firewalls. So most of our firewalls today have this dynamic packet filtering firewall capability, and if it's desired, many of them also have the proxy functionality as well at either circuit level or application level. We'll move forward now and look at the fifth generation firewall. Now this firewall came out in the mid to late 80s, maybe early 90s. There were some of these around. Now the deal is this. Each of these firewall devices are actually sort of like a computer. They have a CPU, a processor, and they also have a program, sort of an operating system that describes how this device is to operate. Well, the operating system is typically broken into two different modes of operation. The more trusted kernel mode, which generally are functions that support the operation of the device. And then we have the less trusted user mode, and those are the functions that something external is trying to request from us, like some other application or process or other thing. Now, the firewalls historically had been operating in the user mode, the less trusted area, because we were trying to protect the functionality of the device itself. And we isolate those functions down in the kernel mode. Now, they figured that the firewall would benefit by adding the firewall functionality down inside the kernel of the operating system. In other words, make this device inherently a firewall at kernel level, and then I don't have to go through this boundary of user mode, kernel mode, and making requests. When the kernel makes up his mind to do something, he's allowed to just do it. The problem, though, is what is this firewall device actually doing? He is isolating a trusted environment from a less trusted environment. And if this device has to handle information flow from this less trusted environment and also handle it at the heart and soul of the kernel, that malicious software that might be coming from that public untrusted network is already in the heart of the kernel, the heart of the operating system, the heart of the device. In other words, it put that dangerous stuff way too close to the heart and soul of your firewall. And while they made these kernel proxy firewalls for about, maybe 5 to 10 years, it soon became recognized that that's just not a bright thing to do. We want to keep that dangerous stuff on the other side of the fence, and only allow interaction through a security filter, that boundary between the user mode and the kernel mode of the operating system for this device. So we don't really see a true kernel proxy firewall in implementation today. Some of the components of the firewall were kept down in the kernel mode, but a rare few, and all the interaction with all the hazardous stuff from the public untrusted network, that's all handled in user mode. So the true kernel proxy firewall doesn't exactly function or exist today. It's more of a historic review of a technology that has since been pretty well discarded. Well, this pretty much completes the analysis of the 5 generations of the firewalls. We're going to look a little bit more about firewall architecture coming up. In this lesson, we're going to be looking at a handful of rules that are commonly implemented on our firewalls. Remember, the firewall is a security device that separates segments of differing levels of trust. I have a private side that is trusted and a public side that is less trusted. Almost always there is a default deny rule built into the firewall. In many cases, it's a rule that can't be deleted because it is one of those core fundamentals. If you were to accidentally delete your default deny rule, your firewall isn't a firewall anymore. It's nothing more than a fancy router. An overblown router is what it is. So the default deny rule says drop everything in both directions unless there's a rule that specifically allows that type of traffic. That's our default deny unless there's an explicit allow rule. Generally, when you're building this list of rules in what we call the access control list, the ACL, you want to keep it as simple as possible. Keep your rules very straightforward, very direct, and if the firewall allows for some sort of built-in documentation, why is this rule here? What is it supporting? Why did we need it? Is it temporary? Is it permanent? Etc., etc. You want to be able to document each and every rule, what it's about, because 3 years from now, some guy named Bobo is going to be working on this firewall that you set up. And 3 years from now, he's not going to know what the heck that rule is doing or why it's there. But if you documented that it's there to support the application web server, then he knows what it is and he knows it has to stay. So document your rules. Always enable logging, and those logs should be sent off to a remote logging repository server. Today, we have many different laws and regulations like PCI compliance and Sarbanes-Oxley and HIPAA and Gramm-Leach-Bliley Act that require certain security components be in place, and they almost all include you have to spin your logs off to a dedicated log repository through guaranteed delivery, secure transmission, hardened bastion host log repository, etc. You need that logging enabled, and you probably want to spin it off to some remote system to store those logs, and perhaps even spin them off through a security information and event management system that will do real-time artificial intelligence to correlate very complex, structured, and slow and low type advanced persistent threat attacks. So we need to enable that logging, spin it off to some place for secure archival, and analyze it. Logging is great if you look at it. If you don't look at it, you're wasting hard drive space. Build yourself a whitelist if your environment supports such a thing. These are the always allow traffic to these destinations because these are the 17 places we always need to go. So don't block any traffic to these locations. It can be nothing but the whitelist where we deny all except the whitelist, or it can be always allow to this whitelist. There's also a blacklist that is a possibility for most firewalls, and this is a list of destinations that we are never allowed to communicate with because they are perhaps known bad guys. It might be my competition. It might be a site that pumps down malicious software and viruses. So the blacklist we can very often download from many different locations on the public internet. A lot of times our firewall vendor will provide us a regularly updated blacklist that we can download and incorporate into our firewall. Along with this blacklist is an area of the internet called the Internet Dark Address Space. So this would be another collection of locations on the internet that we don't ever want our clients to connect to. Now this dark address space is called that because it hasn't been officially allocated by the regional internet registries. In other words, it's an IP address that isn't supposed to be functioning on the internet. Well, what the bad guys do is they figure out what this dark space is, and if they can break into one or two routers on the internet, they can configure the routing system so that these nodes, in spite of the fact the address space hasn't been allocated, these nodes can still be routed to. And so the bad guys will set up their malicious servers in this dark address space on the internet, and we never would want our clients to go there. So along with our blacklist, we might kill off any traffic outbound to this internet dark address space. Another term is this BOGON, and this again is unallocated public IP address space, and again also very often where the bad guys live and breathe and try to draw us to. So the internet dark space and the BOGON space, these are similar in some regard in that it's typically unallocated address space, two different names and perhaps some slight different interpretations on them, but generally we're talking about the same thing. Now these next two filters are typical, should be on every external firewall, the one that is connected to the public internet and connects to your corporate private address space, your private networks. The ingress filter says, because private address spaces in IP are not allowed to operate on the public internet, if an inbound packet ever arrives with either a source or destination IP address that's out of that private IP address space, deny this traffic because it's almost certainly malicious. It probably is an attack on the source IP address that is a private IP address. Somebody on the outside public internet is trying to attack one of my computers on the internal private address space. We don't want this coming through my external firewall. Deny it. That's called an ingress filter because it's inbound. Now, similarly, there should be an egress filter. Egress filter is relative to outbound traffic. Egress implies outbound. Now, on my private intranet, this should be running nothing but the private IP address space. That's a 10 dot something, a 172.16 dot something, a 192.168 dot something. Those are the three private address spaces that should be used behind that external firewall. Now, if I have an outbound packet that has a source IP address that is public, that shouldn't happen because all the nodes on the inside should be using nothing but private IP address space. If a node on the inside sends a packet outbound where the source IP address is from the public address space, this is also probably an attack. And more horrifying is an indication that the node that actually sent this has been compromised, and a bad guy who is now in charge of this computer, called the handler, is actually using this computer on my network to attack some other computer on the public internet. So an egress filter denies outbound packets that has a source IP address in the public address space. These should always be denied. And then, of course, there are a collection of already understood vulnerable protocols, and they're vulnerable for many different reasons. Perhaps the username and password are sent in clear text. Perhaps it's a protocol that's used to scan the network, like SNMP, that implements source routing. It could be another protocol that's used during different types of attacks, etc. Well, any of these protocols that I know are used commonly as attack vectors because the protocol has vulnerabilities, I should deny that type of traffic, especially inbound. And if I care to, I should probably also deny it outbound, but I want to be alerted to it when it goes outbound, because that says one of my guys inside is doing something they shouldn't. So these are the collection of firewall rules that should be implemented on almost every external firewall, the boundary between the public internet and your private segments. We'll quit here for now, and we'll pick up with more firewall information in the upcoming lessons. Let's continue with our review of firewalls, and in this particular lesson we're going to be looking at the architecture. Where should we plug firewalls into our corporate networking environment? So let's look at this diagram now, and let's identify where these firewalls are and why they are here. Let's look in the upper left-hand corner where we see the websites and the public internet. This, of course, is the hostile, untrusted public internet. This is the major source of all of the malware and the attacks that our corporate network environment might be subjected to. The bad stuff we want to stop from coming into our network. As we follow that line to the right, we see that very first firewall there, that little brick wall, and that is my external firewall. Now that's the guy that takes the most abuse. So very often in front of that guy, I'll install a relatively inexpensive router that has an access control list on it, a Generation 1 packet filtering firewall to act as a screening router that drops all of the type of traffic that I would never want to let into my DMZ or my private network. So I'll put a very inexpensive, cheap packet filtering firewall to the left of that first firewall there, and that will knock down a bunch of the garbage that my external firewall would otherwise have to contend with, just wasting his time and resources. Let's put him to good use on only filtering the type of traffic that I might consider tolerating on my DMZ or my private network. So that external firewall is one of my key guys right there. He also is typically running a protocol that we'll be discussing in later sections in this series of lessons called Network Address Translation, that is also closely associated with port address translation. So NAT and PAT are typically always functional on that external firewall. We see to the right of that external firewall a second firewall, and the region between those two firewalls is often referred to as the perimeter network or the demilitarized zone, the DMZ. Now the DMZ is named that because this is a pretty hazardous area. This is an area where we have public-facing services that must access or be accessed by the public internet. That's where all the bad guys are. These guys get taken pot shots at all day, every day. The bad guys are hammered on these boxes trying to break into them all day, every day. So this DMZ is fraught with attacks and bad guys and differing levels of perhaps even compromise. Again, we consider this still be a very hostile area, yet this is an area in my private network space. These are my machines, my servers, my switches and routers that connect these public services together to the firewalls. But again, these are areas where I don't put anything on those servers that I don't want to give away to the bad guys. Don't put anything valuable on these publicly exposed servers. Now, what type of services are these? These are web servers, email servers, FTP servers, DNS servers for my public systems, and things along those lines. So that's the type of stuff that must live there in that DMZ, and these are the guys that are going to get hammered on by the bad guys all day, every day. Now that internal firewall, the second firewall there, that guy is still a very critical firewall for me. That guy's going to have a lot of rules that's going to filter anything from that public space away from my private local area network, my intranet. And so this is where all my trusted computers and computing environment exists, all my resources, all my clients. That's where they all exist. Now, very often, I'll have my users that travel, and they'll connect back to the home office through the internet, through my DMZ, and they'll need to attach to resources on that private LAN, that intranet. Well, I don't want them pulling my sensitive data over the internet in clear text. I'll want them to encrypt all that information, and to do that, I'll have them build a secure channel, a virtual private network. So that one of the first devices we see behind that internal firewall is a VPN concentrator. So anybody who's out in the public internet who needs to access something on the private network will come through the DMZ and attach directly to the VPN concentrator, authenticate securely, establish a secure channel, a VPN, and now they can communicate with these internal private resources. The VPN concentrator will encrypt it before it allows it to flow out to the client, and then it gets decrypted on the client computer, that trusted, authorized client out there on the internet. Next, we see the LAN, and this is our collection of routine resources. These are file servers, application servers, the different types of print services, things that we need on our corporate LAN, our secretaries, our work staff, Other departments will utilize the resources on this main part of our corporate network. However, if any of the information they're accessing is considered more sensitive than routine information on our private networks, like accounting information and our research and development, our intellectual property, the real value for many companies, we would consider those segments, those collections of servers and client computers are touching more sensitive data, more valuable data, and I want to isolate those segments from the rest of the corporate LAN. Remember, that firewall is a boundary between a segment that has a high level of trust, like the accountants in the accounting department, from a lower level of trust, well, the secretaries in the secretarial pool, for example. And so I'll put this firewall in between the accounting segment and the rest of the corporate network to allow another layer of filtering and isolation between the highly sensitive data and processes occurring on that accounting segment and the lesser level of sensitivity and processing of data on the corporate LAN. And similarly, a firewall between the corporate LAN and the research and development department, because again, that's where a lot of our intellectual property is. That's where a lot of the value of the enterprise exists in this R&D area of computing. Now, as we look down towards the bottom and over towards the left a little bit, you'll notice two wireless access points as an example. And if you follow that line back towards the corporate LAN, you'll notice there's a firewall there that isolates the wireless access points from the corporate LAN. Well, you might say, well, those access points, those are inside my building, so those should be trusted. Well, slow down there a little bit. The point is, a bad guy in the building across the street could be attached to your wireless access point. Therefore, always treat your wireless traffic as hostile, because you can't see who it is that's attached to that access point. He doesn't have to come through your front door. He can be in the building adjacent. He can be on the street, in the parking lot, around the corner. And even a bad guy with a good antenna can be 10 miles away and still attached to your wireless access point. So you don't know who that guy is, who is perhaps trying to authenticate and associate to your access points. Always treat that traffic as hostile. So this diagram is a pretty cool but generic map of a good way to implement your firewalls. They are security boundary devices between network segments of higher trust from isolating them from network segments of lower trust. This map here is sort of the architectural overview of the way you want to think of placing your firewalls. We'll quit for now and we'll move forward with the next section of this lesson.